right? Okay, so let us start. And so this is actually the last topic of our discussion for network theory, and this is actually the graph theory. And the other name for this graph theory is the network topology. Right? And this concept of discussion is actually mainly it is coming from the fact that actually we wanted to automate the process of calculating the node voltages and the branch currents. Right? So there this discussion of network topology comes into picture. So if we want to automate the process of calculating the node voltages and the branch currents. With the aid of the computers. The aid of the computers, right? So the network topology comes into picture. Right? Because actually the computer actually can understand only the numbers and digits, right? So that is actually if you wanted to give any information, so that should be understandable by the computer. Now actually how a resistance is discriminated with respect to the inductor in case of the computer, so that actually information you have to be giving explicitly. And first actually how the circuit actually that you are going to give as an input to the computer, and that circuit information actually we will express in terms of this network topology. So how the circuit is interconnected is dependent on this network topology, right? So all these things actually we will discuss in this particular context, and this is not a big topic, this is purely theoretical topic. And so there are questions actually that were coming in this particular context, that's why actually we were discussing this. Now in this case actually first actually we need to understand so certain terminologies actually we will have to understand. Right, so terminology. So because it is there are a lot of new terms actually it comes. Terminology, right? So in this case actually a branch actually, so a line connected between two different nodes. Right, is called a branch. And the second one is node, right? When two or more than two branches are incidented at one particular point, are incidented at one point, then the point is called a node. Right? And suppose actually if there is one node here and there is one node here and there is one node here. Now actually you can connect like this, you can connect like this, you can connect like this. You can even have actually one more connection like this, and you can even have actually one more connection like this. Now this is a graph, right? And in this particular graph, so at this location, so 1, 2, 3. So three different branches are connected to this particular node, and this point actually is called as the node. And anything that is connected between two different nodes, so this is node number 1, this is node number 2, and this is node number 3, and connected between two different nodes. So it can be here, so this is actually one node connected between 1 and 2, and there is one more branch actually that is connected between 1 and 2, and all these lines actually we call these are the branches, right? So these are the branches. But actually how this particular graph comes into picture is, suppose actually I have a resistance here and I have an inductance here, right? And then actually I have a voltage source here, right? And then actually, so there is one more resistance that is connected here. There is one more resistance that is connected here. Now actually this particular information, the circuit information, actually I wanted to feed to the computer. Now in feeding the computer, actually we will have to identify the number of nodes and the number of branches. Then first we will give that information. So these are all the nodes and these are all the branches, and we will feed this information in a matrix format. And then actually between any of the two nodes, actually what was the element that was connected, that will give next. So that is actually first, actually we have to give this network topology, meaning which element is connected between which of the nodes. So how many nodes are there and how the graph looks like. So between two different nodes, actually what are all the different elements that are connected, and what are all the nodes actually that are interconnected. Is there any isolated node, or actually is there any node actually which is incidented with more than two branches? All such kind of information actually you can give it. So this circuit information as it is, it will be given like this. But later actually we will give. So this line actually may be representing the inductance, this line may be representing the resistance, and this line is the resistance, and this line is the resistance, and this line actually it is another circuit element, that is the voltage source. Got it? So like this actually all this information. So these two are actually one and the same. Only thing is actually this actually the real elements that we have noticed, and here actually every element is represented with a line. Whatever may be the element is, be it a capacitance, be it is a resistance, it is an inductance or a voltage source, a dynamic voltage source, or whatever it may be. This is how actually it is represented, and this is what we call as the network topology. So this is the network topology. So this is just the circuit information without actually identifying the circuit elements, right? So simple circuit information actually it will be given. So that is the circuit interconnection information represented as a line for each element. Is called network topology. Right? And this is also called as the graph. Right? So this is also called as the graph, right? And then actually the subgraph. So the graph GS is said to be a subgraph of G if every node of, or every node and branch of GS is part of G as well. Then GS is a subgraph of G. Right? So that means suppose actually you take any particular one. Suppose actually, so there is one node here, there is one node here, and there is one node here. And these two are interconnected, these two are interconnected, these two are interconnected, and this is how actually it is connected. Now actually, I take only this particular portion. Suppose actually these two nodes I have taken, and this is one line, and this is one line actually I have taken. Now in this case actually, every node, so this is actually node number 1, this is node number 2, this is node number 3, and this is node number 2 and node number 3, right? And every branch of this particular graph is part of this graph, and every node of this particular graph is part of this graph. So this is called as the GS and this is called as the G, right? GS means subgraph and this is the main graph. And like this, actually, there can be more than one subgraph. So actually you take this one. So this is also one subgraph. So this actually, you can take it anything. Even this one also actually is a subgraph, right? So anything you can take it as long as actually every node and every branch is part of this graph. So that is the subgraph. Got it? And so tree. So tree of a graph. And this is an important concept, right? So tree of a graph meaning, so if all the nodes connected with branches without forming the loops, is called a tree, right? And a graph actually may have more than one tree. Right? More than one tree. Suppose actually you take this particular graph. Suppose actually there is one graph like this. Now actually, so by definition actually, every node has to be connected, right? So this is node number 1, this is node number 2, this is node number 3, this is node number 4. So every node has to be connected. That is the condition, right? And how many such kind of trees that we can form for this? Can you try to guess how many number of trees we can form? There shouldn't be any closed loop and every node has to be connected. It will be a subgraph, obviously. 3. Any other answer? Let me show you. So suppose actually I take actually 1, 2, 3. So this is actually one tree. So here actually every node is connected, but no closed loop. And then actually this is another tree. So this is 1 and this is 2, right? And then actually one more thing I will draw here. So this is like this, like this, like this, right? So this is 1, 2, 3, 4. Now every node is connected even in this also. Got it? And then actually you take another case. Like this, and this one. So this is also one more, right? So how many we got it? So this is 1, 2, 3, and this is 4. And then 5, right? Six. So this was already there, right? Right? How many we got it? We got 6. Let me show you if more than that. So this is also one graph. And the other way also. So these are actually 1, 2, 3, 4, 5, 6, 7, 8. So did you get actually 8 different graphs actually we formed it, and everything actually satisfies the condition that actually it connects each and every node of that particular graph, and so no closed loop is going to be formed. Got it? Understood? Is this understood? Right? Like this actually there are many possibilities actually that you are going to get it. Now in this case, the importance of this particular tree is, and here actually we will have one more definition. So there is something called twigs. So twigs actually, the other name is actually branches of a tree. Is called twig. So all these branches, so this one actually, so this is one twig, this is one twig, this is one twig, right? So these are actually the twigs for this particular tree. So twigs are related to a particular tree. So the twigs of this tree may not be the twig of this one. Got it? So twigs are related to one particular tree. If you identify any tree, and for that tree actually there could be more than one twig, so one twigs. So this is actually 1, 2, 3. So 3 different twigs are there. So in every case actually we have got in this case actually 3 twigs. And now actually the importance of these twigs is, suppose actually if you take other than these twigs for any particular tree, you can join any other one. Suppose actually I take this one, this tree, and then actually if I join with one particular branch, then actually don't you see that actually this is forming a closed loop? Yes or no? You can take any particular tree, it will always be that particular scenario. Suppose if I take this one, if I join one, then actually it is going to be forming as one closed loop. Suppose actually if I take it here, so here I can take it one link, and then actually it is forming a closed loop. If I take one more link, actually it will form one more closed loop. So every tree actually, if you join with one particular single branch, it will form a closed loop. And this is the new one actually, what we are using to form the closed loop is called as a link. So in this case, actually, this is called as a link, right? So link by definition, link is that branch of the graph which is not the T branch, the tree branch, and the link will make link branch will make a closed loop. So from this actually we can get one information. If you take any particular tree, the tree is anyway connecting all the nodes. Now actually you can use actually the number of links actually you can identify. Each link actually is corresponding to one closed loop. So if you want to form a KVL, then actually the number of closed loop you wanted to identify, right? So to identify the closed loop in any particular tree, we will see actually the links actually how many that are going to be present. That links actually it will be the number of closed loop actually that is going to be formed, right? Now in this case actually, suppose if there are n different nodes, then the number of branches of a tree are how many? How many branches will be there in a tree if there are n nodes? How many branches are there? Try to guess it, no? It is easy only. How many branches will be there in a particular tree? N minus 1, exactly, right? So this is actually, suppose if there are two branches and two nodes, there is only one actually you can take up. And if there are actually three, then actually 1, 2, right? If there are actually three different nodes, 1, 2, 3. So basically 1, 2, 3, 4. 4 nodes, 4 minus 1. And this is 3 minus 1. This is 2 minus 1. So it is always actually the n minus 1 number of branches will be there in a tree. Now how many number of links will be there? So let the total number of branches of the graph be capital B. Then the number of links of the graph or of the tree, we can say. How many links will be there? Number of branches are B. How many links will be there? Yes, how many? It is straightforward, right? Without actually knowing the network topology, you can conclude these information. If there are 5 branches are there, and let us say 4 different nodes are there, and 5 branches are there. 4 nodes, obviously 3 branches will be there, and out of 5 actually 3 is forming the tree. Then actually the remaining 2 will be the number of links, right? Obviously, right? Got it or not? Right? See this actually you can take any particular graph. Let us take the same one. Then actually, so this is 1. Now here 1, 2, 3, 4, 5 branches are there. So B is equal to 5. And then actually in this case actually, yeah, 6 branches we can take it. Right? So 6 different branches are there in this particular case. And then actually the number of branches in a tree. So BT you take it. The number of branches in tree actually 4 different nodes, hence actually 3 branches will be there in a tree. Now the remaining 3 will form as the links, obviously, right? So B minus the number of branches in tree. So this is the links. So B minus n minus 1 is the value of L, the number of links. Got it? Understood or not? Okay. And the next concept is the oriented graph. So first step in the network topology is actually just identify the circuit elements. So identify the circuit elements and which are interconnected to each other, and that we are showing as the line graphs, right? And then actually the next step ahead of that is, so we have to show the directions of the currents or actually the voltages, right? So usually actually we talk about the directions of the current. So for the graph, if you show the direction of the currents, then actually that is called as the oriented graph. So basically, so in case of oriented graph, one is actually we will have to assign right the node numbers, branch names, node numbers, branch names, and assign the directions of the current. Usually the current, if it is node actually we take the voltages, right? Then the resulted graph is called as the oriented graph. Right? So this is called as the oriented graph. Now in this case, suppose actually the same graph we take it. Now suppose actually there is a current that is flowing here, there is a current that is flowing here, and there is a current that is flowing here, and there are actually the currents actually that are coming in this particular case. Now here actually this is the oriented graph. It doesn't matter actually whatever the directions you are going to give it, but as long as actually the directions that were assigned, then this is called as a oriented graph, right? So this is the oriented graph, and along with this actually giving the directions, you will have to notice the nodes also. And you have to give the branches also. Suppose this is branch number 1, right? So this actually we call this as A, B, C, D, E, F. So like this actually you will have to name each and every branch, and you have to put each and every nodes, and usually the convention actually we will give the nodes numbers and the branches actually the branches A, B, C, D, like that actually we will give it. So this is the oriented graph. So this is the oriented graph. Basically, without actually giving these directions on the node names and all, that's actually the normal graph. And this is the oriented graph. Now, this oriented graph actually we will be using to form the incidence matrix, right? So what is this incidence matrix is? So this incidence matrix actually, this is actually specifying the directions of the currents in each of the branches, right? So it specifies the orientation information, or actually there is a 1-1 correspondence between the oriented graph and the incidence matrix. There is a 1-1 correspondence between a oriented graph and incidence matrix. Right, oriented graph and the incidence matrix. That means actually if you give the incidence matrix, then actually we can prepare the oriented graph, and if you give the oriented graph, then we can prepare the incidence matrix. That is how it is. Now what is this incidence matrix is? Suppose actually we take the same graph. Suppose let us say this is node number 1, 2, 3. 1, 2. So this is node number 1, this is node number 3, 2, and this is 3, and this is 4. And the directions actually, let us give these directions. And then actually, so let us say this is the direction actually that was given. So these are actually any random directions that you can give it. Because based on this actually we will do the calculations. In reality, suppose if the current actually what was given in this particular direction, if it happens to be the opposite, then you will get the current value as a negative value. So other than that actually there is no difference. So you can give any random direction, still it is a oriented graph. It may not be the exactly the voltage source is driving the current in this direction, so it may not be that way, right? So but still final result actually it will come as accurately and without having any deviations. Got it? Now to the incidence matrix actually what we do is, and here the branches actually that will be horizontally be there, and vertically actually the nodes will be there, and we will prepare a matrix out of it. Got it? Horizontally branches, vertically the nodes, and we will prepare the matrix out of it. And here the number of nodes 1, 2, 3, 4 nodes are there. So this is node number 1, node number 2, node number 3, and node number 4. And we can give the names for this particular branches. So this is A, B, C, D, E, F. Now these branches actually we will put it horizontally. So this is A, B, C, D, E, F. All right. Now what we do is, for every element if you take it, now every branch actually it has to be connecting to one or the other node, obviously, right? Every branch has to be always in between two different nodes. So then in that particular case, you take the branch A that was connected between 1 and 2. And if it goes away from the node, then actually you give as +1. If it comes into the branch, if it comes into the node, you give -1. Now in this case, for the branch A. So this is for the branch A, and for the node 1, and this A branch actually is going out of the node. So if it is going out of the node, actually you give as the positive because it is driving the current. So that means it is able to provide the current. So that means actually we will give +1 for node number 1 for the branch A. So this is +1. And for the same branch A, for node number 2, it is coming in. That means actually it is taking the current, node number 2. So correspondingly, node number 2 will be -1. And this is the only connection between 1 and 2, and no other connections are there for this particular branch A. Hence, actually the remaining values actually it will come out to be 0. But I hope you understood this one. If you understand this, then you can complete the matrix completely. Is this understood? Right? Now actually based on this understanding, try to complete this matrix. I will anyway complete it, but you do it now. Right? I think you got it. Right? Now actually let me complete this. Yeah, great. So for branch number 2, it is goes out of 2 and comes into 3. So for branch number 3, so this is +1 and this is -1, and the remaining values are 0. And for branch C, so it is going out of 3 and coming into 4. So for branch C, so this is 1 and this is -1, and remaining values are 0. For branch D, so this is the branch. So it goes out of 2 and comes to 4. So out of 2, so this is +1 and comes to 4. This is -1, and the remaining values are 0. And for E, it goes out of 1 and comes to 4. Out of 1. For E, right? Yeah. So it goes out of 1. So this is +1 and it comes to 4. So this is -1. Remaining values are 0. And for F, this is goes out of 1 and comes to 3. So this is 1 and this is 0 and this is -1 and this is 0. Right? And this is how actually you can finish the graph. Right? And now in this particular case, what is the important property that you can see out of this particular matrix? What you can just conclude based on that particular matrix? Can you give me one clue from that matrix what we can always say that it is true? Any idea? Don't you notice that actually the sum of this entire column is 0? This is always true. Right? If you add up all the elements of the column, actually it will always come out to be 0. Even if there are actually two different branches that are there. Suppose actually you take actually this is one branch. Let me add one more branch. Suppose actually if I add one more branch, even then also actually it is connected. So in this particular case only. So even if you give this particular information, let us say I call this as G. Then actually I am adding one more. So this G actually if I add it, then even then also the G actually goes out of 1 and then actually it comes to 4. So this is -1 and 0. Even here also actually it is coming out to be 0. It doesn't matter whatever may be the kind of graph it is, whatever may be the number of branches that are connected between any of the given two nodes. It doesn't matter. It is always the sum of the each and every column is 0 for any incidence matrix. So this is the incidence matrix. So the sum of every column is 0. Right? The sum of every column is 0 for any of the incidence matrix. Got it? And also actually, usually suppose actually if I ask you to solve the network, whatever I have given, so that is actually I have connected a voltage source here and then actually these are the resistances and then actually everything if you treat as resistance, then actually we always take this particular node as the reference or the ground node, right? Suppose actually the same thing actually if you try to put it in case of resistances like this, and like this actually I have given the resistances and between this actually I have connected a voltage source like this, and then there is one more resistance here and there is one more resistance here and there is one more resistance here. If I give this one, our tendency is always actually we will take one particular node as the reference node. So that means I am making this particular voltage as 0. If I take that as the reference node, are we losing any information? If I consider as V versus if I consider that as 0, we are not able to differentiate anything because actually we were getting the complete information without actually losing anything. Correct or not? That's how actually we solve the problem, right? We take one particular value or particular node as the ground and we will try to express everything with respect to that. So that means taking one node out of the network actually we are not losing any of the information. So that is one important conclusion. So by removing one node out of the network, we will not lose any information. And the resulted incidence matrix we call that as a reduced incidence matrix. Reduced incidence matrix. Now we will take what exactly happens actually. Suppose this is 1, 2, 3, right? And then actually, so we will remove the fourth node and then actually we will try to draw the information from there. And this is A, B, C, D, E, F, G. And now actually I take this one and this is actually 1 minus 1 0, 0 1 minus 1, minus 1 0, 0 1 minus 1, and then actually 0 0 1, 0 0 1, 0 1 0 1 0 0, 0 1 0 1 0 0, and 1 0 minus 1 1 0 0, 1 0 0. Now actually this is what we call as the reduced incidence matrix. Now actually by keeping this particular information, are you losing anything? Are you losing any information, whatever is required or whatever is mandatory to solve our problem? Are we losing anything? Yes or no? Right? Without actually giving the network information, without actually giving the any network topology. Suppose if I give just this as the reduced incidence matrix, right? So we are not losing any information out of this. Why? Because let me tell you why. Suppose actually if I give this, if I say that this is a reduced incidence matrix, meaning I have reduced one row out of this. Then actually if I ask you to construct the next row, then actually you can immediately construct it. So suppose actually if I make this 4, without actually knowing the network information, we are constructing this information. If I give this as the reduced incidence matrix, I have given an important property that the column sum is always 0. And now in this case actually 1 minus 1 it is 0. So hence actually this element has to be 0. And this is actually 1 minus 1 which is already there. This is also 0. And 0 0 1 is there. Here actually we have to keep minus 1. And then actually 0 1, so 0 1 0, so this is also minus 1. And 1 0 0, this is also minus 1. And 1 0 minus 1, this is 0. And 1 0 0, this has to be minus 1. So I am able to construct everything, right? I'm not losing any information even if I give only the reduced matrix. I hope you got that. Right? Okay. Yeah. So this is an important understanding, and from the incidence matrix actually we should be able to construct the graph, and from the graph actually you should be able to construct the incidence matrix. Even if you give the reduced incidence matrix also, we will be able to construct the incidence graph. Got it? I hope you got it. Right? Okay. So I would like to stop the class for now, and in the next class actually we will finish this all together. And there is something called tie set matrix and the cut set matrix we have to discuss, and with that actually we'll be done with this particular topic. Got it? In the next class actually, so we will construct this cut set and tie set matrix along with the instance matrix, and then after that actually we will start with another subject. We were done with the networks. Got it? Yeah. So that's all for today. Yeah. Thank you.